All right, so yeah, welcome to discussion 2. Today we'll be talking about algorithm analysis and pseudocode. So let's dive in. So our objectives for today are to talk about time complexity and then space and time complexity and what the difference between them is. And then we're going to have a couple of rules on how time complexity and space complexity or work, how we decide on what the time and space complexity are. And then we're going to talk about how to write pseudocode. Okay, so first of all, time complexity. So what is time complexity? So time complexity quantifies the amount of time taken by an algorithm to run, and it has a function of the length of the input. So you might wonder, okay, well, why is this necessary? Why can't we just take the amount of time it takes for the program to run, right? And that's another way we could absolutely measure it. The reason why we use time complexity is because time complexity gives us kind of an objective measure. So it doesn't so much depend on what your compiler is or what hardware you're running on. So you have slower hardware, or maybe you have like a compiler which maybe isn't as fast, or maybe you're using a slower programming language. You can still quantify how good your algorithm is by using time complexity. So rather than just measuring based on how much time it takes, you can kind of get an idea of how good the algorithm is just based on what the algorithm itself is. That's why we use it. And then there are 3 methods of growth that we typically talk about when we talk about time complexity. So the first one is big O notation. And this is the asymptotic upper bound of a function. So if we think about, if we have a function, right, and it runs in n squared time, then the big O notation of that we could have is big O n squared, big O of n cubed, anything that's an upper bound for how fast our function is. So our function would just run slower than that. Then we also have big omega notation. Okay, well, wait a second. For a given function g of n, we denote big O of g of n. This is how we say its order of g of n, for a given function g of n, big O of g of n is what we say, and then big omega notation is lower bound. So big O is the upper bound, big omega is the lower bound. So if we have again, let's say g of n is n squared, right? Our algorithm runs n squared time. Then we can say that it runs in big omega of n squared, or we can say it runs in big omega of n or big omega of 1. All of those are fine because we're just looking for something that lower bounds how fast our algorithm runs. So as long as we just say, oh, it runs at least this slowly. And big O is saying it runs at least this fast. And then we have big theta notation. And this is the asymptotic type bound. So something is big theta notation, let's say g of n, if and only if it's big omega of that and big O of that. So it's both basically big theta just means it's an upper bound and a lower bound. So it's the actual amount of time it takes. Usually we just refer to big O and we treat it kind of like we treat big theta, but the idea is the same. We're just basically saying, okay, how much time does it take to run? And we're mostly concerned with big O in this course. We're mostly just worried about upper bound of a function, but generally we talk about it as if it were big theta. So as an example, if we have g of n is 5n squared plus 4n plus 2, then big O of g of n, we would say is big O of 5n squared plus 4n plus 2. And these are some of the rules that we're going to talk about. We drop constants. So this 5n squared, we're going to drop the 5. And this 4n, we also drop lower order terms because they're not as important. Because generally when we think of big O notation, it's sometimes useful to think of it, okay, what happens if the size of my input grows to infinity? Let's say n goes to infinity. Well, as we go to infinity, right, lower order terms aren't as important. So we just drop them. So and we don't have to worry constants because again, as we go to infinity, constants don't matter. So we drop lower order terms and we drop constants. So we're just going to say it's O n squared. So these two are equivalent. Okay. And if at any point as I'm talking, you guys have questions, just feel free to stop me. Okay. Next, we're going to talk about best, average, and worst case time complexity. So these are a little bit different than big O, big omega, big theta, because what these have to do with is their asymptotic time complexity. Again, we assume our input size goes to infinity. So that's still true. But the difference is that when we talk about best and worst case time complexity, these have to do with properties of the input. So what that means is for example, if the input is sorted or if the input is unsorted, right, or reversely sorted. then we might want to worry about, okay, what is the time complexity then? So maybe let's consider bubble sort, right? So maybe you guys know what bubble sort is. Do you guys know what bubble sort is, by the way?
Yes.
Okay. Awesome.
Yes.
Cool. All right. So let's say we want to run bubble sort. If we're running it with a sorted array already, like let's say it's 1, 2, 3, 4, and we want to sort it in ascending order, then what we would do is we'd say, okay, 1 is less than 2, 2 is less than 3, 3 is less than 4, right? We don't have to make a single swap. So in the case in which the property of the input is such that it's already sorted, then bubble sort just runs in O of n time, right? Because it just makes one pass of n elements. And in the worst case, right, the worst case is n squared, which is the same as what like our big O notation is. So even saying big O here is weird. Like I would say, yeah, just best case time complexity is just of order n, and worst case is of order n squared. And the big O of bubble sort is still just big O of n squared, because it's an algorithm which does take n squared with inputs, but in the best case it's on, because if the property of the input is such that it's already sorted, then it can only take n. So when we talk about best and worst case, that's properties of input. Like if there's some special way of arranging the input that gives you a better thing, that's what we mean when we say best and worst case. But there's one distinction, and like it can be any property except size. Like if I told you that the size of the input is just 1, right? Or let's say just like 100 or whatever, like for 100 elements, that still means like it's still n elements. Like in that case, we set n to 100. That does not mean anything. Like if I give it a set size, that won't affect best or worst case. So, but any other property does affect best and worst case. So we'll have some questions about that later. So maybe it'll clear it up a little if it's confusing. Okay, moving on. Looking at comparison of time complexities. So as we can see here, like O of n factorial and 2 to the n, like 2 to the n is exponential, right? And factorial is 1 factorial. Those grow really, really fast. So we want to try and avoid those algorithms if we can, because it takes way too long for large inputs. So generally, these other algorithms which take log n or O1 or ON generally are preferable if we can. Some things you just can't do any better than exponential though. This just hopefully gives a good idea of like just how fast they grow. Okay, but we talk a little about time complexity. There's also space complexity, and space complexity is kind of like time complexity, except instead of it being about the amount of time an algorithm takes, it's the amount of space it uses. So if, for example, I need to copy an array, I'm given an array, right, of size n, and maybe we have an array here, has like n elements, right? There are n of them. And we need to copy them all. Then that means we need to copy all n elements. So how much extra space we're going to use? Well, we're going to use n extra space, like or big O of n extra space, because the amount of space we're using with respect to the input, if the input is of size n, then we're also using space, which is of order n, right? So the memory that this algorithm would take would also be n. If, for example, it was just like, I don't know, adding 2 numbers, if maybe I didn't have to use any space except for like 2 variables, one for the first number, one for the second number, and it's just O1 space. Like we would call it O1 because we're only using like a constant space, because we're only using like a set number of variables. So hopefully that kind of makes sense. And okay, so now we'll go to a poll question. Question number 1. The best time complexity for bubble sort is O of 1 if the input array has only 1 element. Is that true or false? So if you're watching online, you can pause and try and answer, but if you're here, you can also try and figure it out. Maybe put an answer in the chat if you want.
True.
Okay. And
So I would say false, because you said that the best and worst case can depend on anything but the size of the input.
Right. Yeah, exactly. So yeah, it was good thinking, Rachel. But yeah, it's that, because like I said earlier, it has to do with, it can be any property of the input except, like as you mentioned, any property of the input except if I tell you it's like a certain size. But yeah, good thinking with you both.
But-
Your
If wait, so is it saying like we can't even think about the size when we're saying best case or worst case?
right, yeah. When we talk about best or worst case, just ignore size because, for example, in this case, even if I say the size is only one element, well, then that's still like, we would still say, okay, like n equals 1, where n is the size of my input. So it would still be O of n. So we don't worry about like size when we're talking about best and worst case. Any other
Okay.
property of the input, it's fine, just not size.
What I was thinking is that like since it only has one element, the best case and the worst case would both be 1. But I guess it's still n. I get it. I get it.
Yeah, yeah. Okay, cool. Yeah. Okay, yes, it's false, as we mentioned. Cool. Okay. So now moving on, we're going to talk about rules for asymptotic analysis. So rule 1 is addition, and we'll go through them. And then rule 2 is drop constant multipliers and so on. So first, addition. So if you have two like parallel code blocks, so like one after another, like sequential loops, so you see here, you add their time complexities together. So in the first one, we have a for loop that goes through n elements, and the second one we go through m elements, right? And this is O of n plus m. And don't mistake this for example, if we have like for, I'm just gonna write I to n, and then indents, so like inside of this, we have like nested loops for j to m, right? Nested loops are going to be different. And the reason why they're different is because we have nested loops, then this inner one, right, is going to do m iterations. But how many times is it going to do that? It's going to do n times, right? It's going to do m iterations n times. So it'll be like m plus m plus m n times, and that's just the same as m times n. Whereas with sequential, like if they're not nested, if they're just separate, then we do this one, which is on. We do this one time. And this one's OM. We also do this one time. So it's just like 1 times n plus 1 times m. So that's why we end up with something like this, ON plus m instead. Okay, so sequential, it's addition, and then if they're like nested, then we multiply. Okay, so that's the first rule. The second rule is we drop constant multipliers. So as we mentioned earlier, right, if we assume that like the size of our input n goes to infinity, right? Then as things go to infinity, we don't really worry so much about constant multipliers. So we just remove it. So in this case, because we don't have like n and m, we just have like n and n. So there are two n's. This first one is like 1 times n, right? Go through n things one time. Second, we go through n things one time. So our total is O of n plus n, which is just O of 2n, right? But again, we drop constants. So O of 2n is the same as O of n. Like these are equivalent. So we just generally say O of n. So drop constant multipliers. And rule 3 is different input variables. So if there are different input variables, like we saw earlier with the addition rule for n and m, here there are different input variables again, n and l this time, right? And just like before, we have n plus l. But notice that we keep both variables in what we say at the ends with n plus l, rather than having like 2n or 2l, because we don't know which one's larger. And so because we don't know which one's larger, we just have to keep them both. Just say n plus l. If maybe we knew like, oh, if we knew L was like less than n, then we could just say like O of n, but we don't. So we just keep it in there. And then the last
Can
rule
you,
is,
sorry, can you go back to the additive? I'm having a little trouble seeing the difference there.
oh yeah, those two slides are actually the same.
Okay.
Yeah, like this slide is the same as the other slide, just different variable name, but it's the same. I'm not really sure actually why those are like split, but yeah, you didn't see them.
All right, thanks.
Okay, and then our fourth rule is drop lowest order terms. So let's just first go over this slide as if this m didn't exist. So let's just take out the m and let's just say this is n. Okay, just for now. We'll worry about if it's m in a second here. So just ignore all of this. This is not important for the time being. So let's just assume this is an n. Then what we would have, right, is this first loop is O of n, right? And the second loop will be O of log n. And it's log n because each time we go through, we're multiplying j by 2. So it'll be log base 2 of n, but it doesn't, well, okay, I'll mention that in a second. But yeah, it's just O of log n, and it is O of n. So if we add them together, if you remember from earlier, if we looked at the little cheat sheet, we realized that O of n grows faster than log n. And because they're both of order, they just both have to do with n, we just drop the lowest order term. So really what we're going to end up with is n plus log n, right, as our big O. But again, because we're only worrying about as it goes to infinity, we don't worry about the lower order terms. So we don't worry about log n. We can just say this is also just the same as O(n). Okay. Now, if it were like n times log n, then we can't drop it because it's multiplied together. So yeah, but if it's just additive, we drop the lowest additive terms. But now we treat it as if we have n and m, so two separate things, right? Now what we're going to end up with is O of n plus log m. Instead of O(n) log n and O(n) plus log n, it's going to be O(n) plus log m. And remember, because we don't know what m is, we don't know the relationship between m and n, we have to keep them both. And that's from the additive rule from earlier, right? We don't know what difference between m and n is, so we just keep both. If someone told us like, oh, they grow at the same rate, or like n grows faster than m, then we would know that like this is at least as small as like log n, or no bigger than log n, and then we could just drop it. But because we don't know, we just say this. Okay. And one final thing I wanted to mention is that when we talk about logs, right, you may have noticed we don't necessarily need to put like log base 2. We don't need to put the base of the log, because with any logarithm, you can change any logarithm to any other log. Like you can change log base 2 to log base 3, or log base 2 to log base like 5, or whatever. Doesn't matter. Using the log rule, right? And like the log rule change is only a constant factor. Like to go from log 2 to log 3, you just multiply by a constant factor. And since we drop constant factors, log 2 and log 3, in terms of big O, are exactly the same. So generally when you write log, basically all I'm trying to say at this moment is when you write log, you don't have to put the base, you just put log. Okay. So those are the 4 rules. And move on to a full question. So yeah, again, if you're watching this like later, you can go ahead and pause here, and otherwise, if you're here, you can try and answer it.
So would this be order n because they're like parallel blocks of code? And even though you're kind of skipping through the loop by a factor of c, that's just going to be a constant.
That's exactly right. Yeah, perfect. Cool. Yeah, so that's great. So just to go over it if you're online, what Wesley was saying was that like for this first for loop, right, we're going through it, and each time we go up by c, so how many iterations we're going to do? We're going to do like n over c iterations. And for the second one, we're also going to do n over c iterations because we just add by c each time. So it's n over c. So big O of n over c plus big O of n over c is just 2n over c, right, total, if we add the 2 up. And what this is going to result with is just, we have a constant factor here of 2 over c. And we can just pull that out and not worry about it because it's a constant, right? So we just end up with big O of n. Okay, so another full question. Asymptotic of this algorithm. And again, if you're online, you can pause it if you're watching like later.
So like your previous example, it's a multiplicative factor, so it's going to be logarithmic.
Yep, that's exactly right. So we notice here, right? Each time we we start at 1, we're going up to n, and we're multiplying by c each time. And so in this case, that's multiplicative. This is just going to be log n, right? And similarly with this one, we start at n, we just divide by c each time. So it's also log n. And again, I'm going to be log base c of n, but we don't worry about the base. So we have O of 2 log n, because we add them up, right? And 2 log n, we drop the constant term up front, and we're just left with O log n. Cool. All right, so for question number 4.
So I'm not quite sure. Like I want to say n cubed, but since they're different variables, then it's probably you're just adding.
Yes, that's
each
good.
loop.
Oh, Rachel, do you have something to say?
Yeah. Like n times m or a times b, whatever variables you want to do.
Yeah, that's exactly right. Perfect. Yeah. So let's go over this. So basically, let's just say that like the size of array A, let's just call it A, and the array size of array B is B, right? Then what we're going to do is notice that these are nested loops. And as we mentioned earlier, when you have nested loops, you're going to multiply out, or generally kind of multiply out. Let's just start at the most inner loop. So the most inner loop is runs in time big O of 100,000, right? It's a lot of zeros. And then the next loop, this inner one, right, runs in time of O of B, right? And the most outer one runs in time of O of A. Because we go through every element in array A and every element in array B. And how many times do we do the most inner loop? Well, we do it however many times this one runs times 100,000. So we run this one 100,000 times however many times we run, like this one here. And this one here, right, we run B times however many times we run this one. Well, this one we run A times, this one we run B times. So far, A times B times 100,000. So we end up with AB 100,000. And here, we just drop this constant term. Even though it's large, we still drop the constant. And so we're just left with big O of AB. And if we look at the answer here, that's what we have. So 100,000 is still a constant, even though it's large. We drop the constant multiplier, so we end up with AB. And now move on to the next. And yeah, again, if you're online or watching asynchronously, you can pause otherwise. So. And this one's kind of a tricky one. We can just go over it if you guys want. So for this one, the way we do this, right, is we look at this outer loop first, right? And the outer loop runs n times, right? And then the inner loop we have to figure out, right? So let's just try and find out how many times do we actually run the inner loop. So the first time through the inner loop, right, we have I is n, right? And if I is n, we go from 0 up to n. Because we start with j0. Let's just actually start. Like let's keep count of I and j. First time, I is n, right? And in that case, j goes from 0 to n. So how many times does the inner loop run? Well, it's going to run n times. And then I becomes n minus 1, right? So j is going to go from 0 to n minus 1. So now j is going to run n minus 1 times. And then when n is n minus 2, j goes from 0 to n minus 2. So we have plus n minus 2. And we keep going until finally I is 0, right? So we're just going to keep going. And it's the same pattern up until like I is 0, right? So plus 1 equals 0. So do you guys know what this sum, what order this sum is going to be of?
n.
And so you're close because like this is n, right? But notice we have to figure out first of all how many terms they're going to be, sort of. So this sum, let's rewrite the sum. So this sum is the same as saying like the sum from I, or from 0, I equals 0, so 0 to n of, let's just say I equals 0 of I. And another way of writing this is we can like group the terms. So we have n is going to be paired with like this one here. So we have an n minus 1 is going to be paired with like the 2. So this sum is actually equivalent to n plus 1 over 2, or n times n plus 1 over 2, because they're n over 2 terms, right? If we group like the largest one, n, with the smallest term, which I guess would be 1, like excluding the 0 for a second, we can pair the n with the 1, the n minus 1 with the 2, the n minus 2 with the 3, and so on. And each of those sums is n plus 1, and they're n over 2 of those terms. So this is actually equivalent to n plus 1 times n over 2, which is then just equal to n squared plus n, and both of them are over 2. Again, we drop the lower order term, and we drop the constant factor. So we're just left with n squared. And so that one is kind of tricky. But if you see it, something like this, just maybe keep note to yourself. Okay, so this outer one is of order n, and the inner one depends on that outer one, right? So you can kind of just think, okay, I'm multiplying, right? But this one is n, and this one depends on the I. So when you see something like that, it's just generally n squared. But for this particular type of problem, if there's like no logarithm stuff, it's going to be n squared. So this is the like math behind it, is the stuff on the lower part of the screen. But in general, you can kind of see that and look at it, and you know, it's kind of tricky. So yeah, that's how we get n squared. And if you guys have questions about like anything I went over, absolutely just ask. And otherwise, we'll go to the next questions. So how about this one? What's the complexity of this question? This one's tough too. So yeah, good. If you're, again, asynchronously watching, you can pause here.
So there's at least log n, and the only option that has log n is n log n. So that's my guess.
That's a good reason to guess that, actually. Believe it or not, so this one's actually a really trick question, because like this one's a bit of a trick question. So this one specifically is just something that, like, if you see this specifically, it's like the only time when you have like log n, which you may not get log n out at the end. But in general, that is a good rule of thumb to follow. Like if you see one that's log n, it almost always include log n. But let's go through kind of the math and see where it takes us. So, okay, so this outer loop, right, runs n times. So the first time, or not n times, it runs log n times, like you mentioned. The first time, let's just note what I is. So the first time I is n, right? And the first time also, j starts at 0. So j starts at 0, and it goes from 0 up to n. So we go from 0 to n. And so that means this inner loop, we're going to run n times. So you have n. Okay, And then the next time through, I becomes n over 2. So now I is n over 2. So j runs from 0 to n over 2. So we're going to have n plus n over 2. And the next time through, we divide I by 2 again. So now we have n over 4. So we have n plus n over 2 plus n over 4. And then we keep going until we finally hit this n condition, I is 0. So we can just keep going, n over 8, n over 16, n over 32, and so on, all the way until we get like I is 1. So we'll just do 1. And this sum can also be expressed this way. So maybe if you recognize this, it should be like I equals 0 to n. Well, it's going to be like n over 2 to the n, something like, or oh, it'll be, we can pull an n outside. So it'll be something like 1 over 2 to the I and just n. And yeah, it won't quite run to n, it'll run to like log n. But the idea behind this is, even just like ignoring this summation here, if we just look at this, the idea behind this is this sum, if you may recognize it, because it's just all the powers of 2. And if as n approaches infinity, if we sum all the powers of 2, like 1 over all the powers of 2, so 1 over 2 to the I, actually, yeah, if we just like let this go to infinity, even like I equals 0 to infinity, this here, right, this sum is bounded by 2. So here, even if we let n go all the way to infinity, we're going to get 2 n times an n out front, so 2n. So for infinite many terms, this sum goes to 2n, and we drop the constant factor, so we're just left with O(n). And so this question makes it very tricky.
That's a good one.
Yeah, it's a tough one, for sure though. But there really aren't so many other trick ones like this. In general, if you see something that's log n, it's almost always going to include a log n, except for like this particular case. So even if like you want to memorize this case, that's fine. Something else that's interesting is no matter what constant this is, as long as this is a constant c, you're going to get the same result, where it's just O(n).
So do you recommend, like, if we have nested loops and it looks like it's something that depends, like the inner loop depends on the outer loop, we should really kind of work it out? Because yeah, just trying to estimate it, you could easily kind of go the wrong way.
Yeah, I think it's definitely good to try and work it a little bit. And if it looks like it isn't so complicated, like if both of them, yeah, right, like this one, it's j depends on I. But if maybe it doesn't depend on I, if it just depends on n, then it doesn't matter. But this is kind of an unusual example. Usually when you have the first one depends on the second one, it's going to be something more like this. It's just this case. But yeah, it's always good to like at least work through it a little bit. Okay. All right, so for poll question number 6, yeah, again, asynchronous open pause here. Yeah, what is this one?
Just order 1, right?
Exactly, right. Yep. This one's just order 1, because even though this is like large, if we like big O of some constant c, it doesn't matter what it is. That's just always equivalent to O of 1. Awesome. So we look at the answer. Yeah, O(1). Cool. Okay, question number 7. So I'll, I guess, try and do both, I guess. So, yeah. And then we'll go over both answers at once.
I'm not up to date on my logarithms, but I think the second one is same time. I'm guessing A is faster for the first. I don't know.
Okay. Rachel, do you have any ideas?
By grows faster is less efficient.
Grows faster, yeah, less efficient.
So I would say B and then C.
Okay. And I think Wesley might have like mixed up like.
Yeah, I think I did.
Yeah. But yeah, both of you got that, had exactly the right idea with that. Yep, and we see the answers here are exactly as we said. Because log x and we're taking an extra logarithm on x, then it's going to grow more slowly, right? Than just log x. So the graph is going to be, for log x will look like the values of y are bigger for every log x. And if the second one, they're the same, because as we mentioned earlier, the way you get from log 3 to log 2 or vice versa is you just have to use change of base formula. When you do that, you're just going to get some constant multiple that's tacked on in front. And with big O notation, we drop constant multiples. So it doesn't matter. Big O of log base 3 of x, big O of log base 2 of x are the same growth rate. Okay, so now for question number 8. Which of these belong to the family of big O of n squared?
B, C, and E, or sorry, B, D, and E.
Yeah, so that's right, because when we say big O, right, for big O notation, we want this to be the upper bound, right? Like we want n squared to be the upper bound for whatever we're choosing. So all of these have to have a slower growth rate, and the only things that have slower growth rate are log n, or n log n, and 5 9. That's right. Okay, so what if I said instead of big O, if I said big omega, and if I added an extra answer choice, like let's say answer choice F, which was just n squared, then what would the answers be?
ACF.
Yep, that's exactly right. So with big omega, right, we're looking for lower bounds, and it can be a tight lower bound, so that's perfectly fine. So F is fine because it's the same growth rate, so we can totally use it. And A grows faster, C grows faster. So n squared is slower or equal to AC and F. So that's what we choose. But okay, for the original question, it was B, D, and E. So that's why we see those highlighted. Yeah, awesome. Okay, so now I have a discussion question. So this one is something we're just gonna go ahead and like briefly talk about a little bit. And we're not gonna like work out a solution in code. We're gonna talk about it a little bit. So what would the time complexity be for an algorithm that counts the number of A's in an array of strings of unknown length? So if you guys can think about that a little bit.
So it sounds like a nested loop because you have a number of items in the array, and then each of the array items is a string that you have to iterate through.
Mm-hmm. Yeah, that's some good thinking. That's exactly what I would have said myself. So perfect. Yeah. So right. So just to expand upon that a little bit, like with an example, but perfect. If we had an array, right, it has, let's say, n strings, right? And I don't know, we don't know the length of any string, but let's just say that the longest string length is like m. So maybe I have a really long string length. I don't know how long it is. Let's just say it's like m. And I also have n strings. Well, in order to find the number of A's, I have to go through every string. So which there are n of them. So n strings times the length of each string. Well, the length of each string is upper bounded by m. And for big O notation, that's perfect. We just want the upper bound. So it's big O of n times m, right? So O of nm basically is what we're going to wind up with. That's our big O. Because just as you said, we're going to need a nested loop, one to go through each string and one to go through like the array of strings. Now, if we maybe knew ahead of time, like that every string is of length 10, then what do you think our big O notation would be in that case?
That's linear.
Right, exactly. Mm-hmm. Because then in that case, like this m just becomes 10, we drop the constant factor, we just end up with O of n. Perfect. Yeah. And so let's just review the answer here. Time complexity for an algorithm is O n m. But if we limit the length of the string, then we can consider it a constant and drop it. And yeah. And that's something also to keep in mind, like if you're writing your own program, it's sometimes important to keep in mind that sometimes even provided methods and libraries do take time. So testing equivalence of strings, like with dot equals, if we don't know the length of the strings, that still is an operation which takes like OM time. So you have to actually make a comparison. Okay, cool. So now we've finished with algorithm space and time complexity. And now we're just going to talk about pseudocode. And so pseudocode, so for example, if you ever have to write like on an exam, if we ask you to write code in like a text box, then we're not going to like expect you to write code with perfect syntax because that's silly. So we just expect you to write pseudocode, which is just kind of like code, but it doesn't have to be perfect. It's just as long as you get your point across, that's the main point. So we're just going to talk about like some general rules for it. So you ready for that? If you have like that on a test, which at some point you probably will on a test in this class. Okay, so yeah, on paper or online in text box, this just sucks. Like having to write this out, like this would be Java code, but this is like insane if we actually expected you to write this without an IDE or compiler. And different languages have different constructs. So we're not expecting you to follow even like a specific language construct as long as it's like a general idea and like we see exactly what you mean, then you're good. So abstract algorithm structures, again, it doesn't have to compile. So this would be actual like runnable code. But what if for FizzBuzz in particular, but we can make it better. We can make it more readable. So it's better for like pseudocode. So how can we write pseudocode to be more clear? Well, you don't necessarily need curly braces in pseudocode. You can just use indents. And so that's one thing. You don't necessarily need access level and you don't need method declarations unless, of course, like the methods, unless we actually ask you for like a method declaration, like you wouldn't need something this verbose. Maybe you could just have like main instead of like public static by main string args, right? And you can replace any standard library methods with a simple verb. So instead of like system.out.println in Java, or instead of cout, std, cout, endl in C++, you could just do something like print. So this is just a simplification of what we just saw. Rather than all of this, it can just become this. Again, notice no curly braces. We have our for loop, we have else if, and all of that. It's just, and print instead of println. It's just a lot easier to read even, and probably easier to write as well. So we can stop there, but you can also go further if you want. As really, I guess the main idea is like, as long as what you're doing like is reasonable, like can be transferred into code, and also like you're consistent, like you don't say, oh, in one case you're not like, oh, print, in another case you're not like cout. As long as it's just consistent, it doesn't really matter that much. But the whole idea is just be more compact. So, but also instead of doing like if I mod 3 is equal to 0, you could write something like if I is divisible by 3, because that's also fine. So it could look something like this. If I is divisible by 3, rather than saying if I mod 3 is equal to 0. As long as the point gets across, you're good with pseudocode. So yeah, it's just written in plain terms. Generally, you want to keep some keywords like for, if, else if, because those have some meaning behind them. But you can, instead of saying like using modulus, you can say divisible by. That's fine. And you can use like end for instead to show where you're ending the indent. But you can also just use end indents, like you can stop indenting. That's fine too. Yeah, and some hard rules. Just be consistent. I think that's the biggest one. Just be consistent with whatever you choose to do for pseudocode. As long as you're consistent, you're good. And stick with a certain style. So again, that's just consistency. Test your code. So this is a good one, actually. Like if you have on an exam, you have to write code. My suggestion is always just when you're done writing your pseudocode, or as you're writing your pseudocode, just come with random examples in your head and just like go through your code and make sure it's actually doing what you want it to. Because if you don't have access to like an IDE, then it's a little harder to make sure that it's actually working. So go ahead and like test it if you have to write pseudocode. And yeah, that's about it. You write your abbreviations down clearly. And yeah, software rules. I think some things don't matter. Like I don't care if you put like ++ or I++. And yeah, again, this is just consistency. And yeah, ternary is kind of weird to read. So if you want to use it, you can, but otherwise don't. That's the same thing in regular code though. And this is just another example. It kind of follows the same pattern as before, but otherwise it's the same. And you can use pros. So you can use like set current node equal to head rather than current node equals head. That's okay too. And same thing for data structures, algorithms, data structures, all the same. And yeah, like I said, just be consistent. That's it. Yeah, and I think you guys have an honor log quiz due like sometime. I don't remember, but yeah, you have an honor log quiz. Make sure you do that. Or maybe it's not honor log, but you have a quiz. That's about it. That's the end of the discussion for today. If you guys have any questions, feel free to ask them.
Thank
Otherwise,
you.
yeah, no problem.
Thanks.
Sure thing.